Hello everybody, this is Dr. Christopher White and welcome back for part 4 of Mesozoic Earth History. So now we're going to have a look at Mesozoic Sedimentation. So we're going to focus on the location and types of sediments which are being deposited on North America during the Mesozoic. Excuse me. So the eastern coast and core of North America had a pretty consistent depositional regime throughout the Mesozoic. So for most of the time, these areas were above sea level, so you're going to have a system dominated by terrestrial sedimentation, so you're going to have things like fluvial sediments and desert deposits in these areas. Now, you are going to get submarine deposits being put down, and of course they're going to occur along the east coast. For most of the Mesozoic, the east coast of North America is a passive continental margin, so we're going to get the standard sandstone, mudstone, limestone marine assemblage. Now, in contrast, the western side of North America has a far more complex history during the Mesozoic. So on the western side we have a mixture of volcanic rocks, passive marine marginal rocks, so that's sandstones, mudstones and limestones, terrestrial sediments, so that's desert deposits and river deposits, and deposits associated with shallow empiric seas. And of course all of this sequence is then going to be deformed by major orogenic events, so it's a very complex area. Now, sedimentation along North America's western margin during the early Triassic was dominated by shallow marine sandstones, shales and limestones. So that's the classic passive continental margin sequence. So of course we know the Sonoma orogeny will be finishing by the early Triassic, and of course once it finishes, the western side of North America becomes a passive margin. Now, in the middle and late Triassic, we see the sea along the western margin of North America regressing, and this exposes the shelf marine deposits. So it exposes these sandstones, mudstones and limestones that were deposited in the early Triassic, and so they get reworked by terrestrial processes. So we have fluvial processes and desert processes reworking this material, and we have the occasional small marine transgression. So the sea will come onto the land for short periods of time and then it will regress back into the ocean basin. Particularly during this time period we have a lot of red beds being deposited, so this would imply a hot, arid, desert-like environment. So what we're going to do now is we're actually going to run through the major sedimentary units for the western United States from the Mesozoic, and we're going to interpret what each of these units is telling us about the environment. So I should point out, by the way, I've just noticed I made a small change to the presentation, but I didn't update this here. So can you just ignore this line right there, please, and pretend it doesn't exist? So what does the sedimentary sequence along the western coast of the US tell us about the Mesozoic? So we're going to start with the lower Triassic, so the early Triassic Munkapi Formation. So it's a red and brown mudstone with mud cracks, ripple marks, fossil amphibians and reptile tracks. So this is interpreted as a fluvial system. We also have thin beds of marine limestone, indicating there were small sporadic marine transgressions, and we also have evaporite beds within this sequence, indicating that every once in a while you'll get an isolated body of water that would evaporate away. So what we're looking at is a hot, arid environment covered by persistent large rivers. So that's then followed by the late Triassic Shinarump conglomerate. Now you might notice the middle Triassic is missing, and that's because it's been eroded away. And the Shinarump conglomerate is therefore essentially represents this erosional surface. So the late Triassic Shinarump conglomerate is pretty widespread. It unconformably overlies the Munkapi Formation, and it's indicative of a period of erosion. So we've completely lost the middle Triassic rocks. So the Shinarump is then followed by the Chiln Formation. If we come over to this diagram here, we can actually see the formations we're talking about. So we've started with the Munkapi Formation, and the Shinarump conglomerate is going to be there along that interface. Then that's followed by the Chiln Formation. Now this is a mixture of shales, siltstones and sandstones, and these rocks contain petrified wood, they contain amphibian fossils, they contain crocodile-like organisms, and they contain small dinosaur fossils. So this is interpreted as being once again a fluvial system cutting across a desert environment, so much like the Munkapi Formation. So the Chiln Formation is then followed by the Wingate Sandstone. This is a clean, well-sorted sandstone with crossbeds. This is a classic desert rock. And then that's followed by the Kientem Formation. So that's a mixture of sandstones, shales and limestones. It contains ripple marks and crossbedding. The sandstone beds contain well-sorted quartz sands. The formation represents essentially a channel system, so most of the sands are representing river channels. The muds represent the floodplains, and every once in a while we do get these limestone formations, which once again hints at small marine transgressions producing shallow bodies of water, which are pretty well suited for limestone deposition. So what you can see at the moment here is as we move from the Triassic into the early Jurassic, we are maintaining this hot, dry environment, but this environment is also cut by large river systems. So it's not a completely dry desert, it's a desert environment, but nevertheless it has a ready sources of water cutting across it. So after the Kientem Formation comes the Navajo Sandstone. This is a well-sorted quartz-rich sandstone, displays very large crossbeds which suggest big dunes, and it contains dinosaur and crocodile fossils. So it's a desert deposit, and the fact that we do have the crocodile fossils tells us once again we do have persistent bodies of water in the environment, though, because crocodiles do obviously like to live in water, so that their presence in the area tells us there must have been persistent lakes or persistent rivers in which they could live. So by the Middle Jurassic, the Navajo Sandstone gives way to the Carmel Formation, and this is a mixture of mudstones, limestones and lesser sandstones. The layers display ripple marks, marine invertebrates, and rare dinosaur tracks, and so this is interpreted as a shallow marine environment. So the mudstones, the limestones and the sandstones are displaying ripple marks. That's probably due to wave action, and the invertebrate fossils are telling you you're dealing with an environment that's either going to be shallow marine or maybe coastal, so possibly some kind of beach environment. Now, the presence of the dinosaur tracks obviously tells us that these areas must have been exposed for periods of time. So what we're looking at here is we're looking at a coastal environment where the sea level is shifting. It could possibly be a tidal shift, so it could be daily, or it could be the types of shift that happened on a longer time scale, marine transgressions and regressions. And so by the time we're into the Carmel Formation, we're into a coastal situation. So this would imply the sea level is rising in the area. By the Middle Jurassic, we have a mixture of the Entrada Formation is from the Middle Jurassic, and it's a mixture of sandy mudstones displaying herringbone crossbedding, and well-sorted sandstones displaying symmetrical ripples, asymmetrical ripple marks, and crossbeds. So what we're looking at here is we have essentially a sequence of rocks that is representative of tidal mudflats, so that's the herringbone crossbedding. Beach deposits, those are the symmetrical ripples, and shallow marine environments, those are the asymmetrical ripples and crossbeds. So once again, we have a situation where we are in a coastal environment, and we can see that the sea levels are such that sometimes we are in an intermediate setting, like a tidal mudflat or a beach, and sometimes the sea level rises for periods of time, and that leads to the deposition of shallow marine deposits. So after the Entrada Formation, we enter the Curtis Formation. So this is dominantly a sandstone sequence, displays crossbeds, ripple marks, and invertebrate marine fossils, along with lesser mudstones and limestone. So this is showing us it's a shallow marine environment, so we're underwater. Now, we also have gypsum deposits as part of this sequence, so that would imply that every once in a while portions of this body of water became isolated, evaporated away, and that's going to lead to the deposition of gypsum. So once again, we are in a shallow marine environment, and we're getting these sea level changes occurring, and sometimes these sea level changes will result in bodies of water becoming isolated and eventually depositing evaporites. So the Curtis Formation is followed by the Somerville Formation. So this is a mixture of mudstones with lesser sandstones and gypsum beds. We see mud cracks within these muddy sediments, so that's obviously telling us we've got mud drying out. We also see dinosaur tracks and other fossils. So it's interpreted as what's called a Sabkha environment. So this is a muddy environment that exists along the margins of hypersaline bodies of water. So think of a body of water that's evaporating in a desert environment, so it gets very, very saline. while along the margin of that evaporating body of water, you're going to have the buildup of muds. And this is going to form what's called a sabkha environment. So the presence of this sequence here is showing us we have a large body of water along the edge of along the modern-day west coast of North America. This body of water essentially is isolated or partially isolated. It's evaporating away. We're getting these hypersaline conditions appearing, and it's leading to the formation of this muddy deposit along its margin. Now, by the late Jurassic, we have the deposition of the Morrison Formation. So this is a mixture of sandstones, mudstones, shales, and rare conglomerates, and this is related to the Navajo Orogeny. And so these sediments are being produced by erosion of the mountain range that's forming. And so that explains the large quantities of conglomerates, these very coarse sedimentary rocks. These rocks are being interpreted mostly as fluvial systems within both elevated terrain and exiting elevated terrain onto an arid plain. So essentially we have high ground which is being actively eroded, the sediment is coming off that high ground and it's being deposited into an arid environment, so a desert or semi-desert system. Now, as we enter the early to middle Cretaceous, things begin to change. So during the early Cretaceous, we have a marine transgression taking place. So we have essentially water coming in from the south and from the Arctic, and this produces the Moray Sea. And this transgression continues into the middle Cretaceous. We have the eroding highlands of the Navajo and the Seaver orogeny being actively eroded, producing large quantities of clastic sediment at the same time. So what we end up with essentially is a Pyrrhic Sea into which we have large quantities of clastic sediment being formed by the erosion of the highlands associated with the Navajo and Seaver orogenies. So this leads to the formation of what's called a clastic wedge, which is a large triangular shaped package of rocks. And this clastic wedge contains sandstones, mudstones and conglomerates. Now the wedge will thin and fine to the east. So if we look at our wedge, it's thickest on the western side and thinnest on the eastern side. And we also see there's a steady change in the class size as we move from the west to the east. So on the western side we tend to find quite coarse sedimentary rocks, so coarse sandstones and conglomerates, and as we move eastwards the coarse conglomerates will grade into sandstones, the sandstones will grade into mudstones, and in some locations on the eastern side the water quality actually became good enough for the deposition of carbonates. So this is our situation here. So here's our Pyrrhic Sea. We obviously have our high ground over here that's going to be actively eroded, and that's going to produce plentiful sediment which is going to be deposited along the western margin of our Pyrrhic Sea primarily. So we're going to have lots of sediment being deposited on the western side, and obviously on the eastern side we're going to have less sediment being deposited. This obviously explains the approximately triangular shape of the body of sediment, because we've got loads of sediment on the western side and the amount of sediment steadily decreases as you move eastwards. So we have the deposition of substantial quantities of mud which are being produced by the erosion of the high ground. But at the same time we have a body of water here that's relatively warm and relatively shallow, and so it's going to be absolutely stuffed with photosynthesizing single-celled organisms. And so these single-celled organisms, when they die, are going to be incorporated into the mudstone, and so what you're going to end up with is a very, very organic rich mudstone. So we're going to see the formation of black shales as part of the sequence being deposited within this Pyrrhic Sea. Now, by the late Cretaceous, the Moray Sea joined with a marine transgression from the south, which emanated from the Gulf area, and this produces a continuous seaway which runs from the Arctic up here to the Gulf down here, which we call the Cretaceous Interior Seaway. At its widest, it's going to be about 1,500 kilometers in width, and it splits North America pretty much into two land masses. So the eastern margin of the seaway received little detrital sediment and was on the whole dominated by carbonates. So along this side of the Cretaceous Interior Seaway the water quality was pretty good, the water was relatively shallow and warm, so carbonate precipitation along the eastern boundary is possible. Now, the western boundary, on the other hand, is still receiving large quantities of clastic sediment, which are being eroded from the highlands over here. And so this obviously means we still have the deposition of conglomerates, sandstones, and mudstones in those areas. So when we look at the sequence itself, we actually see that there are variations in the sediment supply going into the Empiric Sea. And this causes intertonguing of the clastic sediments. Now, the changes in the rate of sediment supply are interpreted as being due to changes in the rate of uplift. Typically, the faster something is being uplifted, the faster it will be eroded, and so the more sediment it will produce. So when this happens, when we have large amounts of sediment being produced, being deposited in the Empiric Sea, it causes the clastic wedge, essentially, well, the coarse rocks in the clastic wedge, to push eastwards into deeper water because there's more sediment. As the rate of uplift slows down, we have less clastic sediment being produced, and we see finer sediments moving back westwards. And so this produces this kind of zigzag pattern, this intertonguing within the sedimentary sequence. So we can see the diagram right here. So here's our clastic wedge. We can see it's going to be thickest on the western side, and the wedge is going to thin as we move eastwards. So what we can see is we can see our wedge consists of a number of different sedimentary types. So in the kind of reddish brown here, we have conglomerates and very coarse sandstones, these Arco sandstones. Then as we move into the orange, we have just standard sandstones. Then as we move into the yellow, we have shales, and then this purple-blue layer here represents limestones. So this is showing us as we move from west to east, our class sizes are steadily decreasing. And of course, this makes sense. You know, we have sediments coming off the high ground over here. The coarsest sediments will be deposited first. Then the intermediate sediments will be deposited, and obviously the finest sediments will go the furthest. And so we'll have the muds towards the east. Of course, as we've discussed, sometimes on the eastern margin, the water quality does become good enough for the deposition of limestones. So the sediments change from conglomerates and coarse sandstones on the west to finer sandstones, siltstones, and shales in the east, as we just discussed. So the detrital sequence terminates and transitions into shallow marine limestones and chalks on the eastern margin, where the water quality is on the whole pretty good. So during the periods of active mountain building, rates of erosion pick up, and this causes the wedge to push further east. And so during periods of increased erosion, we will actually see the facies moving eastward. So we can see how in this instance, we can see the conglomerate here is definitely stepping out. This is showing us this is a period of increased erosion, more sediments coming into the basin, and so the conglomerate facies starts to push eastwards, and we can see a corresponding movement of the sandstone facies eastwards over here as well. So as the Cretaceous draws to a close, the seaway begins to retreat both north and south, and marginal marine and terrestrial deposits move in, leading to the formation of coal-producing wetlands. So our Empiric Sea begins to drain. For a period of time, we have a very swampy, boggy environment. Once again, the climate is still hot though, so this is the perfect condition for the formation of coal swamps. And then eventually the sea will continue to retreat even further, and then these coal swamps will be replaced by terrestrial environments, and we'll return back to our very hot, dry desert system, which are cut by large, persistent rivers. So the final thing we're going to think about is how important was accretion to the growth of the western coast of the US, or should I say North America in general. Now, much of the material added to the west coast of North America during the Cordilleran Orogeny was detrital sediments, which are being eroded due to the uplifted ground. These are deposited on the continental shelf and into the oceans. And of course, these detrital sediments are the result of the erosion of older continental crust. So a lot of the material being deposited along the western coast are simply clastic sediment eroded from the highlands. Now we have additional volume being added by intrusion, so we've already discussed how these felsic and intermediate magmas are moving into the thickened crust associated with the Nevadian and Seaver orogenies, and as we've also touched on, a lot of this magma will never make it to the surface to be erupted, so most of it gets stuck underground, it cools, solidifies, and it produces plutonic rocks, particularly granites and diorites. So The analysis of many mountain systems has identified that they are not only made from accreted sediments, sedimentary rocks and plutonics, but they also contain what are referred to as small lithospheric blocks, which will have formed elsewhere, and they will have been transported in essentially on the oceanic crust, which is subducting under the continental crust. So these blocks are referred to as terranes. So they are distinct from the other rocks of the Cordilleran Orogeny and North America in general, because we can see they have differences in their fossil content, their stratigraphy, their structural trends and their paleomagnetic properties. And so these properties do not match the rocks which are forming in North America at that time, and so we can therefore only come to the conclusion that these rocks are from another location and they have moved over and sutured onto the side of North America. So in many cases the differences are so clear that it's been suggested that they could have been actually carried very great distances before they collided with North America. So more than 25% of the Pacific coast, so that's going from Alaska all the way down to Baja California, consists of these accreted terranes. They do make a quite substantial input to the the development of the western coast of North America. So the terranes that we see consist of volcanic island arcs. Well, that makes sense. We know that North America will run into several island arcs during the Cordilleran Orogeny. We have rocks related to ocean ridges. Well, we know that the oceanic crust is subducting down underneath the continental crust, and so we know we are going to have rocks associated with ocean ridges being subducted, and so some of those rocks will get accreted onto the side of North America. We have seamounts, which are extinct volcanoes on the seafloor. Once again, not really a huge surprise that those are present. We have volcanic plateaus, so these are areas of raised seafloor which are commonly associated with large flood basalt eruptions which are taking place on the seafloor. So you end up with these big, thick, flat sequences of mostly basalt. Once again, we see those present in the terranes, and we also see small fragments of continental crust. And so all of this material essentially represents rocks which are being scraped off the subducting oceanic crust. So it's estimated that there are greater than 100 different sized terranes that have accreted onto North America's western margin during the last 200 million years. So this is obviously quite a long period of time, but we know the vast majority of these terranes will have actually accreted onto the western side of North America during the Mesozoic as part of the Cordilleran Orogeny. So the terranes, along with the felsic intermediate intrusive rocks, essentially help to add new volume onto the western side of North America. And then, of course, that's on top of the rocks which are being formed as part of the erosion of the high ground and the deposition of clastic sediments. But that's more of a recycling process rather than the addition of new rock. Okay, that's it for the presentation. Thank you for your patience and sticking with me, and have a good day.